So, we will discuss the mean value theorems, Rows theorem, Lagrange's mean value theorem and Cauchy's mean value theorem, generalized mean value theorems. Yesterday we have discussed about the local maxima and local minima, and we have seen a function f defined over a interval all metric space x d. F is a function which is real valued and defined on a metric space A. Then we say f has a local maxima at a point P if there exists a delta such that the value of the function at the point P is greater than the value of any number q which lies in the delta neighborhood of P. If it lies in the delta neighborhood of P, and if the image of any point q is less than or equal to the value of the function at P, then we say function f attains or has a local maximum at P. If there exists, P belongs to X, if there exists a delta such that this inequality holds for all q belonging to this, that a d of p q is less than delta. Similarly, when we say it has a f has a local minima at P belongs to capital X, if there exists a delta such that f of q is greater than or equal to f of P for all q with d of p q is less than delta. So, this is the case of local maximum or local minima, and in intervals in a similar way, when we say a function has a local maxima or at the point A, it means there is a neighborhood x minus delta, x plus delta such that whenever any point t lies in L, then f of t is less than or equal to f x for all t belonging to this range, if it has a maximum local maxima, and similarly for the local minimum. So, with this we have a result which is useful in establishing the mean value theorems. The result is, let f be defined on a closed and bounded interval a b, and if f has a local maximum at a point x belongs to the open interval a b, and if the derivative f prime x exists at this point, then the derivative must be 0. So, what it says is if the function attains a local maxima at a point x in the interval a b where the function is totally defined, and also the derivative of the function at the point exists, then derivative must be 0. Okay. The same case is the similar statements. Similarly, if let f we define on the closed interval say a b, and if f has a local minima at a point say x belonging to a b, and if the derivative of the function exists at this point where it has a local minima, then the derivative of the function is 0. So, this is the condition that at the point of local maxima or local minima, if it attains and the derivative exists, then the derivative must be 0. Okay. Let us see the proof of this. The proof is Suppose the function f, which is defined on the closed and bounded interval a b, has a local maximum at the point x belonging to the open interval a b. Okay. Suppose, let us see. So, what definition of this? By definition of the local maximum, there exists a delta greater than 0, such that the functional f of t will remain less than or equal to f x for all t belonging to the neighborhood of x, that belonging to this, that is, this is the point x, and here we are having the neighborhood x minus delta and x plus delta. So, if the function a attains a local maximum at this point a, then corresponding to this we can identify a delta and a neighborhood such that whenever the t lies here, then the value of the function is also less than equal to x, or t lies here, the value of the function will also be less than equal to f x. Okay. So, if suppose t lies between the left hand interval of x, then the ratio f of t minus f of x over t minus x. Now, since t lies between this left hand interval and function attains the local maximum at the point x. So, f of t will be less than equal to f x. So, this part will be negative and t is less than x. So, again this part is negative. So, total is greater than equal to 0. So, this implies that limit of this as t tends to x of this quantity, that is f of t minus f of x divided by t minus x, which gives the derivative of the function at a point x, is greater than, or it cannot be negative. Therefore, the derivative f prime x is greater than equal to 0. This is the first part. Now, if the t lies between this interval right hand towards the right of x, then the ratio f of t minus f of x over t minus x. When t lies here, the f t is always less than equal to f x, because x is the point, a local maximum point, and t is greater than x. So, this is positive. So, this will be less than equal to 0. Therefore, taking the limit as t tends to x of the same f of t minus f of x divided by t minus x will be less than equal to 0, and that will imply the derivative of this is less than equal to 0. So, 1 and 2 combined will give you that derivative will be 0 at that point. So, if it is a local maximum, the derivative exists, then it has to be 0 there, or if it is a local minima and derivative exists, then it. But if the derivative does not exist, then also the function may attain the the maximum minima also. So, that is what we have the corollaries here. As a corollary, we can say the corollary says that if that is, if let R, let F is a mapping from the I to R, I is an interval, be continuous, on an interval, I, and suppose that F has a local extrema. Extrema, when you use the word extrema, means either local maximum or local minimum. So, one word is used for that, extremum. So, if it has a extremum means either it has a local maxima or local minima. So, if it has a extremum at an interior point, say x belonging to I, then either the derivative of f does not exist or it is equal to 0 if exist. So, this part we have already shown, is it not, that if the function attains the local maxima or local minima and if the derivative exists, then at that point the derivative has to be 0. Okay. Now, what it says this result is that once it has a extrema minimum point, the point of the extrema, the derivative will either will not exist or if it exists it must be 0. So, this part way, for example, for this if we look the function f x which is equal to mod x on the interval say I, which is closed and bounded interval -1 to 1. Okay. Then if we look this graph of the function, the graph of the function will be this here is -1, here is +1. So, 0 is a point which is a local minimum point 0. Therefore, 0 clearly the x equal to 0 is the point of local minimum point. In fact, it is a minimum point. Okay, minimum point, that is minimum point of this. The reason is when you take any point closed in the neighborhood of the 0, if you picked up any point of this, then the value at the point 0 will always be less than equal to value at any point, arbitrary point in this neighborhood. So, 0 becomes the minimum point or local minimum we can say. But the function f x minus f 0 divided by x as x tends to 0, that is nothing but what? Mod x by x when x tends to 0, that does not exist, that we have already discussed, because when x is positive the value will come out to be 1, when x is negative the value will come out to be -1. So, the limit does not exist. So, the derivative is not defined, it does not exist, but the point correspond to a minimum point of it. So, this is one of them. Okay. Now, this is the one way we have discussed it, okay, that if the function attains the local minima, it has to be. So, the criteria critical points we can say. So, as a note, the critical points means if the function f is such, the set of all points, where either derivative does not exist or equal to 0 are known as the critical points. So, obviously, the critical points are only the point where the maximum minimum may occur. So, this is the way of a function is given. First, we will find the derivative. If it exists, put it equal to 0. So, you will get the set of points which are known as the critical point, and then we have to test the local maxima and local minima at this point. It means, if the function the point is not a critical point, then there is no question of discussing the maximum minima. In fact, there will be no maximum minima will be occur at the point other than the critical points. So, that is the important part here. Now, we come to the result that is called the generalized mean value theorem. or also known as Cauchy's mean value theorem. Cauchy's mean value theorem. Cauchy's mean value theorem. What this statement says, if f and g are continuous, real functions, on the closed and bounded interval a b, which are differentiable in the open interval a b, then there is a point x belonging to the open interval a b at which f b minus f a over g b minus g a is equal to the derivative of the function f prime x over g prime x, f prime x over g prime f. Of course, here we are we will take up two cases when g b is different from g a and g b is not equal to g a, that we will take. So, g b is not equal to g a, and they are continuous function, and it is where the g b is different from g a. Okay. Derivative will be because that we will say it is not required, but we will just put it why it is not required, that we will come to when we go for the Rows theorem. In fact, the Rows theorem says that if the g b equal to g a and g is a continuous and differentiable, then there must be some point where the derivative will vanish. So, derivative vanishes means this denominator will be 0. So, it is not defined at all. So, obviously, this is true, we can say. In fact, this will come forth. Okay. Now, here one thing which we can judge, we do not require the differentiability of the function f or g at the end point a and b, because we do not need, we need only the derivative of the function in the interval a b, okay, in the point interior to a b. Now, let us see the proof of this. Let us consider a function h t as f of b minus f of a multiplied by g t minus g of b minus g of a into f of t. Okay. Consider this function. Now, to prove our results, what we want, that there exists a point, in order to prove the result 1, we require to show that there exists that the derivative of the function h dash x 0 for some x belonging to the open interval. This we needed. Okay. So, case 1, let us say if our function h is a constant function. Once it is a constant function, then obviously the derivative of this function will be 0 for every x belonging to the open interval a b. Hence, the result follows. Okay, nothing to prove. Now, case 2, if h is not constant, if h is or st is not constant. Okay. Let us take the two cases. suppose h of t is greater than h of a for some t belonging to the open interval a b. This is our closed interval and t is somewhere here. So, the image of the t at this point is, say here, this is our h a and here is somewhere, say suppose h t is there, okay. And let x be a point on the closed interval a b at which h attains its maximum value, okay. It attains maximum. Now, why it is so? The reason is because this will exist, because h is giving to be this function h we have defined like this, f t minus f a g t minus g b minus into f t. F and g both are giving to be continuous over the closed interval. So, h will also be continuous over the closed interval a b. H, g and f is differentiable over the open interval. So, h will also be differentiable over the open interval a b, and since h is continuous over the closed interval a b and closed and bounded interval. So, it will attain its maximum value and minimum value at least at some point in the interval a b. That result we have seen. Every continuous function on a closed and bounded set will attain the maximum or minimum and minimum value at some point. So, because h is continuous on a closed and bounded interval, say a b, so it will attain at some points attain its maximum and minimum value over the interval a b, that is, okay. And so, we can get it x belongs to this. Now, we have seen here is a b, the point x over a b, this is first. Since we have taken h of t is greater than h of a. So, obviously the point x will not be a point, it will be in the interval a, and in a similar way we can say it is lying between a b. So, x lies between this, okay. Now, further the function h is differentiable inside the interval a b, differentiable at each point in the interval a b, at each point in the interval a b. So, in particular the derivative h prime x exists. Now, use the previous theorem. The previous theorem says this result we have proved that if the function, if f is defined over a closed interval a b and f has a local maximum at some point and the derivative exists, then the derivative must be 0. So, according to the previous theorem, so by the previous theorem, the derivative of the function at this point must be 0, and this will implies that f of b minus f of a is into g prime x is equal to g of b minus g of a into f prime x wholes. Similarly, if we assume if H t is less than H of A for some t belonging to the interval a b, then the same argument by the same argument, then by the same arguments applies to the function h, which attains its minimum value at the point x. Hence, we get this implies we get the derivative h dash x will be 0 in a similar. So, derivative of this 0, and this proves the result. Okay. So, this is very now this theorem, which we call it as generalized mean value theorem, in fact, it is as a particular case we can derive the our result for this function for Lagrange's mean value theorem and Rows theorem. So, next result is we get Lagrange's mean value theorem. What this theorem says is, if f is a real continuous function on the closed interval a b, which is differentiable in the open interval a b, then there is a point x belonging to the open interval a b, at which the f of b minus f of a equal to b minus a into the derivative of the function f prime x. The proof follows from the previous theorem. Take g x is equal to x, and the result follows. So, the result follows immediately. Then come to the next, what is the meaning of this? Let us the geometrical meaning of the Lagrange's mean value theorem. What does it show? That suppose we have this function f x over the interval say a b, say here is a, here is suppose I say b. Okay. Now, let us take another graph, because that is very is a and b. It's okay. Let us take this graph, then it's more clear. Okay. Suppose I take suppose I take this graph. Okay. Here is say a and this is say b. Okay. So, this point is correspond to say like this. Now, if I draw the chord joining these points, this is the chord, the slope of this chord a b is nothing but what? F of b minus f of a over b minus a. This is the slope of this chord. So, what this result says is that if a function f, which is continuous function over the closed interval a b and differentiable in the open interval a b, then there will exist a point x in the interval AB such that the slope of the segment joining the endpoint of this curve will be parallel to this line on the curve. That is, this slope of this and slope of this same. This is the slope is equal to f dash x. This is the slope of this, and here this is the slope. So, both will coincide. So, what this Lagrange's mean value theorem is gives that result regarding the slope. Now, this is the case when both f a and f b are equal. So, we can choose the Rows theorem later on. Okay. Now, from here we can also derive the results which is known as the Rows theorem. The statement of the Rows theorem is, suppose that f is continuous, if f is a real continuous function on the closed and bounded interval a b, which is differentiable in the open interval a b, which is differentiable in the interval a b, and that the value of the function at the end point coincides, f a equal to f b and say equal to 0. We can even take without 0 also it will work 0. Then there exists a point x in the interval a b such that the derivative of the function at this point is 0. The proof follows again from the Lagrange's mean value theorem. In the Lagrange's case, if we take f a equal to f b, then implies the derivative of the function must be 0 for some x belonging to the interval a b. That is, again the meaning is, suppose we have a curve, say suppose we have a curve of this type, say like this, and here is the point a, this is the point say b. Function is continuous and differentiable over the open interval, and at the end point both are attaining the same value and equal to say 0. Then there, according to this, there will exist a one point x where the derivative vanishes, f dash x will be 0 at this point, means the line is parallel to axis of x, slope will be 0, So, this shows the result for them. Okay. Now, using this we can come to now consequence of this result, mean we can get one more result. What this result says is, suppose f is continuous, on the closed interval I, and f is differentiable in the open interval I, at each point in the open interval I, and the derivative f prime x equal to 0 for every x belonging to the open interval a b, then f is a constant function. And obviously, the proof is very simple, because if we apply this theorem, Lagrange's mean value theorem, then over the interval we get x. So, proof is apply Lagrange's mean value theorem over the interval say a x. There exists some point say a x is already there. So, let us take the point a by okay, a by or a t. Let us take the point a t, where the t is lying between a less than b. Okay, t is this over this interval. So, apply this, then what you get is f of t minus f of a equal to t minus a into the derivative. So, there exists a point x belongs to the interval a t, which is of course subset of a b, such that this result hold. Okay. Now, if at this point it is 0, but this is given that the derivative vanishes for every x belongs to the interval a b. So, this implies that f of t equal to f of a, and for every t, but t is arbitrary, So, this implies the function f is constant function, and as a consequence of this result we can say as a corollary that suppose f and g are continuous, on the closed interval a b, and differentiable, and they are differentiable on the open interval a b, in the open interval a b, and they satisfy the condition that f prime x equal to g prime x for all x belonging to the interval a b, for all x belonging to the interval a b. Then there exists a constant c, then there exists a constant capital C, such that the difference of this is equal to c, means they differ by a constant. So, proof follows immediately. So, I will not go for this proof further. Okay. Now, using this thing we can also derive the results for the functions which are monotonically increasing and decreasing. So, suppose that f is differentiable, in the open interval say a b, then the following results holds. Then number 1, if f prime x is greater than equal to 0 for all x belonging to the interval a b, then f is monotonically increasing. B, if derivative f prime x equal to 0 for all x belonging to the a b, then f is constant, which is already shown, and C is if the derivative of the function is less than equal to 0 for all x belonging to a b, then f is monotonically decreasing. Okay. The converse is also true here. If I take here, the converse also hold, that if f is monotonically decreasing, then the derivative will be negative. The converse is also hold, and here also converse hold. Okay. So, we can proof is very simple. just we take the choose the interval say x 1 x 2, choose x 1 x 2 where x 1 and x 2 these are the points of the interval a b for some x being x 1. Okay. Then apply Lagrange's mean value theorem. Then f of x 2, this is proof for a, f of x 2 minus f of x 1 is equal to x 2 minus x 1 derivative of the function f for some x belonging to x 1 comma x 2. Okay. Now, it is given the derivative is greater than 0 for all x. So, this is given the derivative f prime x is greater than 0 for all x in the interval a b. So, this implies that f of x 2 is greater than or equal to. So, it is greater than or equal to f of x 1 when for x 1 satisfying this condition, x 2 is greater than x 1. Okay. So, this shows the function f is monotonically increasing function. Okay. Monotonically increasing function. The converse of this also true. The converse of it, the converse also holds. Why? Because suppose f is differentiable, suppose that f is differentiable and increasing monotonically increasing in the interval I or on the interval I, which is say our a b, I is the interval a b, okay, on the interval I. Now, take a point for any point t which is different from x in I. We have f t minus f x over t minus x. Okay. Now, if I take this is the point x, here I am taking an interval suppose, and t is point somewhere here. If t is in this interval, then x is greater than t. So, t minus x will be negative, is it not? T minus x will be this limit of this when t tends to x, because this limit exists, it is differentiable and it is the derivative of the function at a point x, and since it is a monotonically increasing, so f t will be less than f x. So, since f is monotonically increasing, so f of t is less than f of x for t lying between this say interval a b here. Okay. So, this is less than 0, this one will be less than 0. So, this entire thing will be greater than equal to 0. So, it is greater than equal to 0. If t lies between this interval, then what happen? This will be, if when t lies in this interval, then already t minus x, that is equal to what? This will be greater than equal to 0, because x will be here, is it not? So, we can write it f t is f of x is less than f t. So, this is positive, this is positive. So, this holds. So, basically this holds, therefore, the result follows. Result follows. Similarly, for the second case we can go. So, we are not going to Now, here is a remark. We can say a function f is said to be strictly increasing on an interval say I if for any points x 1 comma x 2 in I such that x 1 is strictly less than x 2, then we have f of x 1 is strictly less than f of x 2. Then we say the function is strictly increasing. Now, when we prove the converse part of the previous result, the note is the converse part of the previous theorem. The converse part of the previous theorem is not true. That is, if the function is strictly increasing function, that you cannot say that derivative will be strictly greater than 0, okay, but strictly greater than 0. For example, if we take the function f x which is x cube from R to R is strictly increasing on R, but the derivative of the function at a point 0 is 0. Okay. So, what we say, the function will not be strictly. So, here the function f prime x is strictly greater than is not satisfied, though the function is strictly increasing function. So, that is the important point which I will. Second remark which I wanted to give it, and it is interesting also. The remark says, when we say the function is increasing at a point, then it has no meaning. Then it means there exists some neighborhood in which the function is increasing. So, when we say a function is said to be increasing at a point if there is a neighborhood of the point on which the function is increasing, on which the function is increasing. Okay. So, at increasing means if the derivative is strictly positive, then the function is increasing at this point, this is also. But just by looking the derivative at a point we cannot decide, but just by looking the derivative of the function f x at the point we cannot decide its increasing or decreasing character That is if when we say the function is increasing at this point, so if the derivative is strictly positive at a point, then the function is increasing at this point, if this supposition is false, then one cannot say that the function is strictly increasing. Function is increasing at that point. For example, suppose I take a function g x which is defined as x plus 2 x square sine of 1 by x if x is not equal to 0 and equal to 0 if x is equal to 0. Okay. Now, this function, the derivative of the function g prime 0, the derivative g prime 0 is g x minus g 0 over x minus 0 limit x tends to 0. So, that comes out to be what? 1 plus limit of this x sine 1 by x as x tends to 0 and this limit comes out to 0. So, we get g prime 0. So, g prime 0 is 0 which is strictly positive, but this function g is not increasing in any neighborhood of 0. Okay. It cannot be. This can be seen easily. Suppose this is the neighborhood of 0 and I take this neighborhood. Consider the point, say here the point I am choosing as x equal to 1 by 2 n pi, and also here another points I am taking as sorry, it is positive. So, let us take, it is okay. Let us take another point x is equal to 1 by 4 n plus 1 pi by 2. Now, both these points clearly choose x such that x is either this or this. Then the x goes to x tends to 0 as n tends to infinity. So, these are the points in the neighborhood of 0. So, x belongs to the neighborhood of 0 with a suitable radius, say delta, that I am not. But what is our function? The function derivative of the function, the derivative g prime x. What is this value? If we look the derivative, the function g prime 1 upon 2 n pi, what is the function is this. Okay. So, when at this point when you find the derivative of this g dash x is function, because the derivative g is this function x plus 2 x square sine 1 by x when x is not equal to 0. So, when you differentiate it directly, you get 1 plus 4 x sine 1 by x plus 2 x square cosine of 1 by x into minus 1 by x square, is it not? Now, the value this g prime x comes out to be 1 plus 4 x sine 1 by x and minus 2 times cos 1 by x. Okay. Now, you see, if I take at x equal to 1 by 2 n pi, the derivative g prime x, this is the any integral multiple of sine is 0. So, sine 1 by x becomes 0. So, this part is not there. Cos of 1 by x, when you take the multiple of pi 2 pi, then it is always be cos 0 is 0, cos 2 pi is 1. So, it is always be 1. So, value will be minus 1. So, it will be negative for at this point, and if we take x equal to 1 by 4 n plus 1 pi by 2, then in that case what happens is at this point the function g dash x, g has a derivative negative. So, at this point the function g has derivative that is g prime x will be positive. Why it is positive? Let us see. If you look the for odd multiple of pi by 2 with n is equal to 1 to 3. So, in fact, when n is 1, 5 pi by 2, 7 pi by 2 and so on. So, this will be odd multiple of pi by 2, this will go to 0. So, there and here it will give the positive values 1, is it not. So, we are always getting the positive value. So, this is always good positive when n is a positive integer, n belongs to n, n belongs to n. So, it is positive. Therefore, in the neighborhood of the 0, the derivative is negative as well as positive. So, neither you can say it is increasing function nor it is decreasing function, although the function which we have taken g prime is 0 at the point 0. So, what conclusion is, if the derivative of a function at certain point is positive or negative, we cannot conclude its increasing nature or decreasing nature until we are sure that in the neighborhood the function has a character for increasing or decreasing. That is all. Thank you very much.